In the last video, I've talked about a semiconductor and how in a semiconductor the valence and conduction, empty conduction bands are quite close together, close enough that the thermal energy from the vibrations of the atoms is enough to excite some electrons, to give energy to some electrons, enough energy to the electrons in the valence band to allow them to jump up into the conduction band, and therefore when the electrons are in the conduction band, when there are some electrons there, these electrons can conduct electricity. So that's how a semiconductor can become conducting. The higher the temperature, the more electrons you get up there, and the more conducting it becomes. But if you go all the way down to 0 Kelvin, then there will be no thermal energy, and then it cannot conduct electricity. Now there is actually a way to make the semiconductor more conducting, and it's through a process known as doping. Now first, let me just mention the most common example of a semiconductor, and possibly the most important: silicon. Probably all heard about silicon these days. Let me spell it out properly. SiLiCon. Or Si is the symbol. Silicon. It's used in all our computer chips. So let's see how we can make it more conducting. Now, I'm going to try to explain this, but unfortunately, the ideas are really a bit abstract and not what we are normally familiar with from everyday life, or even other parts of A-level physics. Okay, so we have this picture in which we have a valence band that is fully filled, my valence band, and conduction band that is empty. And we have say a solid silicon. Okay, let's say I have a piece of silicon. Now there are lots of silicon atoms in silicon. Okay, lots and lots of silicon atoms, of course. And then the electrons in each atom fill up the valence band and leave an empty conduction band. Okay, so that's what we know about the bands, and they're close enough together for thermal energy to excite electrons, but usually not that many electrons get excited, so it's slightly conducting. And so it's a semiconductor. Okay, so that's the situation right now. It's semiconductor that we have. Now what people have done, people have tried many ways to change its conductivity. I'm just going to look at one or two examples. I'm going to look at this example where a small amount of phosphorus atoms are introduced, are mixed into the silicon, just maybe a tiny percentage. So it's like impurity, right? Phosphorus impurity. In fact, that's how it is often described. You add a little bit of this phosphorus impurity into a piece of very pure silicon. Okay, and the effect of this is that phosphorus would introduce some electrons into the conduction band. Okay, the ideas are a little bit abstract, and let's see. Now I'm going to try to explain this in a very simple way, which if you have learned some chemistry, it'll be easier to understand. If not, then you might just skip over this minute or two of the video. Now the idea is that silicon, let's see, a silicon atom has 1, 2, 3, 4 electrons in its outermost orbit, or outermost shell, as it is often called. Now, what these electrons do is that they would share with neighboring silicon atoms. So each silicon atom would have 4 electrons in the outermost shell. So they would share with the electrons from the other silicon atoms, so that around each silicon atom there would be 8 electrons. Now, if you remember from the earlier video, for the second shell of an atom, for the second orbit of a hydrogen atom, 8 electrons will make it 4. Okay, so it is because of some of these ideas and reasons that they like to do this sharing of electrons, because that will allow it to form bonds which joins the silicon atoms together, and that's how the solid is formed. Now, if one of the silicon is replaced by a phosphorus atom instead, now phosphorus atom would have 5 electrons in its outermost orbit or shell. So that means that after sharing 4 electrons with the 4 neighboring silicon atoms, it's got 1 extra electron. It's got 1 extra electron that is not shared, and this makes this extra electrons is able to move around freely, and that, in a very simple sense, is how phosphorus can contribute electrons to this silicon solid. Okay, so that's all I'll say about this idea of how phosphorus atom contributes an electron. But how it affects the conduction band is really quite complicated. So the only thing that I will describe here is to say that the phosphorus, the effect of introducing the phosphorus and producing the extra conduction electron is that the additional conduction electrons that are introduced has an energy level that is just below the conduction band. Okay, the phosphorus introduces an energy level that is just below the conduction band, and the electrons that introduces is in this band. But this band is very close to the bottom of the conduction band, and that just means that the thermal energy would have no problem exciting the electrons from there up to there. Okay, so in this way, phosphorus can supply electrons to the conduction band in a piece of silicon, and therefore make the silicon more conducting. And this process of increasing the conductivity of silicon is called doping. Doping means adding some impurity to the silicon. Okay. Now, but this is not the only way of doing the doping. There is another way. And The other way is to add another type of atoms, in which instead of giving an extra electron after doing the bonding with the other silicon atoms, there is another type of atoms with fewer electrons, so that by introducing, say, something like aluminum, okay, that's the other example, and also have aluminum instead of phosphorus. Aluminum. So if aluminum atoms are introduced instead, now aluminum only has 3 electrons in its outermost shell, unlike the phosphorus atom. So introducing the aluminum would actually introduce a shortage of electron. Okay, because silicon has 4 electrons in its outermost orbits, aluminum only has 3. So introducing aluminum will have the opposite effect to phosphorus. It would end up with a shortage of electron. And what it does to the conduction and valence band is rather strange, to say the least. Okay, we have this conduction and valence band once again. Okay, now when we introduce aluminum, let's say that's the aluminum atom, the fact that there's a shortage of electron would introduce an energy level just above the aluminum. Sorry, let me say that again. The aluminum atoms, introducing aluminum impurity into the silicon, would introduce an additional energy level just above the valence band, very close to it. So a very small amount of thermal energy would allow electrons from the valence band to jump up into this energy level. So the electrons from here will jump up to here. Okay, but this part does not become conducting as a result. What becomes conducting is that the effect of the electron jumping up here is that it leaves behind it means that this valence band in a way is no longer fully occupied if electrons has jumped out of it. So you might imagine that it leaves behind empty spaces in the valence band, right? There's some empty space there, so it's no longer fully occupied. Now, according to our rule of thumb, which says that all the occupied bands must be full in order for it to be an insulator, if some of the electrons has jumped out, then it's no longer fully occupied, and therefore it will become more conducting. Now, these empty spaces that are left behind as a name is called a hole. So it's like a shortage of electron, and each of these holes actually behaves like a positive charge. Okay, so that's what I mean when I say it's a very strange situation. So the so-called hole, meaning the empty spaces left behind, behave like positive charges. And if you pretend that they are positive charges with the same charge as the electron but opposite sign, if you pretend that they are positive charges, you can actually use the same ideas that we know from currents, from electricity, from circuits, and maybe Ohm's law and so on, to actually calculate the currents due to these holes. So you can just pretend that these are actually positive electrons. Right, so these are holes, and those are still called electrons, right? If we used phosphorus instead. Okay, so these are two very different situations, right? One contributes more electrons, one contributes a shortage of electrons, which we call holes. But in both cases, they would make the semiconductor or make the silicon more conducting. But because of these two very different nature, we have names for them. For aluminum, for the case of aluminum, or for there are actually other elements which have the same effects. So for elements that produces holes or shortage of electron or holes, these are called P. Let's write the color. These are called P-type semiconductors. P-type, and you might guess P stands for positive, and that's because the shortage of electrons are like positive particles, which we call holes. And you might guess the name for the other type is called N-type, because it's got extra electrons. Okay, the N here stands for negative. So these are called this type with this that are doped, right? Doped with say phosphorus impurity, or there can also be other elements that can introduce extra electrons like this. So this type of conductor is called N-type semiconductor.